Okay, we're working with the same set of data as before. We had determined the order of A and B using table logic, but now I want to show you an alternative method called the math way. In case the numbers are not so nice and you can't do this mental math easily in your head. So method number 2 involves the math way. So pretend that we didn't do any of that stuff before and you don't know what M and N are. You don't know the orders of A and B. So we're going to start the same way. We're going to write our generic equation. Rate is equal to K times concentration of A raised to some power and B raised to some power. You're going to locate 2 experiments in which the concentration of one reactant is held constant and the other one is changing. And I'm going to choose number 2 and number 4 again because A is changing but B is being held constant. So what I want to do is take all my information for experiment number 2 and plug it into our generic rate expression here. So I'm going to take rate of experiment number 2. So I'm doing experiment 2 over experiment number 4. Okay, and I'm going to plug in the data and we're solving for reactant A. Okay, so the rate for experiment number 2 is 2. I don't know K, so I'm just going to simply write that down. But I do know the initial concentration of A is 0.24 raised to some power of M times the concentration of B, 0.12 raised to the power of N. And we're going to divide that by everything that we know about experiment number 4. Its rate is 0.5. That's K times 0.12 raised to the power of M times 0.12 raised to the power of N. And you'll notice that K's, I got one on the top and one on the bottom, those cancel. And I purposely chose experiment 2 and experiment 4 because the concentration of B was the same. They're both 0.12. So the 0.12s cancel along with their exponents of N. So all I have left is 2 over 0.5 is equal to 0.24 to the M over 0.12 to the M. So I'm going to simplify here. 2 over 0.5 is 4. And then 0.24 over 0.12, that's 2. And that's going to be raised to the power of M. And then I solve for M. 2 to what power would give me 4? M must equal 2. So therefore, this is second order with respect to A. So I've just used the mathy way to solve for the order of A, and we're going to repeat this for reactant B. So reactant B, I need to choose 2 experiments in which A is remaining the same, but B is changing. So I want to choose experiment number 1 and experiment number 2. Sorry. So again, experiment 1, experiment number 2. And I always like to choose the one that has the higher rate, the bigger rate, and put that one on top, and then the one that's smaller, put it on the bottom. So this is going to be experiment number 1 divided by experiment number 2. And I do the same thing as before. I plug in the rate, which is 8 for experiment number 1, baby K times 0.24. Now that I know the power for A, I'm going to go ahead and plug it in. It is a 2 times the concentration of B, 0.48, raised to N. All of that divided by what we know for experiment number 2 has a rate of 2. That's equal to baby K, 0.24 squared times 0.12 to the N. And so the K's cancel once again. the 0.24s cancel along with their exponent of 2, and I simplify. 8 over 2 is 4, and then 0.48 over 0.12, that is also 4, to the nth power, n equals 1, because 4 to the first gives me 4. So therefore, this is first order with respect to b. And so the rate law would be rate is equal to baby k times the concentration of A to the second times the concentration of B to the first, and the overall order would be equal to 2 plus 1, it would be third order overall. So you have two options for solving for the orders. You can choose the math way, which is really helpful when the numbers are not so nice, or you can choose the table logic way, which is helpful for multiple choice questions when you have really nice numbers. But if you choose the table logic way, make sure that you explain using these words. You have to tell me how the reactant concentration is changing, how the rate is changing, and that you held all the other reactants constant.